So in a previous lesson we were estimating the derivative of a function from its tangent line. And the problem is that estimating the derivative of a function from the slope of its tangent line on a graph is very imprecise. And a major achievement of calculus was to develop a set of rules so that if someone knows the equation of a function, they can find an equation that will give the exact value of the derivative of that function for any value of x. How they did it, I'm going to show you in just a second. So pause the video if you still need time to write this down and start it up again when you've finished writing. So what mathematicians wanted to do is they wanted to find the slope of this tangent line to this curve right here at this little dot. Unfortunately for them, they weren't able to find the change in y over change in x at a single dot because that dot, well, it was only one thing. There wasn't any up or over that could be done. It was infinitely small. But what they were able to do is they were able to find the slope of a line between two different points. So let's say over here. They could find the slope of this line just fine. The simple change in y over change in x. Now, what they discovered was that they could start bringing these 2 points closer together. So bringing that point B closer and closer and closer and closer to point A. And notice that as long as there are 2 points, we can continue to calculate that slope. You can see it over there on the right. And so what they were looking at is they were looking at the limit of this slope as B gets closer and closer and closer to A. So if we go back and we look at it, 1.7 goes 2, 3, and then after it gets to 3, it starts slowing down. And it keeps getting closer and closer and closer and closer to, if we were to actually be able to put those two dots right on top of each other, it would closer and closer and closer to 4. And while mathematicians of this time period didn't have fancy computer programs to calculate slopes for them, they did have a knowledge of limits, and they were able to find this limit as dot B gets closer and closer to dot A. What is the slope of that line getting closer and closer and closer to? Let's record what we just saw in the demonstration. So really how they did it, how they found the rules for the derivatives, is they took the limit of the slopes of the secant lines. The secant line just goes through 2 points where the tangent line just brushes at 1 point. Mathematicians found the limit of the slope of the secant line as the points on the function got closer and closer together. So moving from this first green line, this first blue line, finally to this purple line, notice that the slope of the line is getting closer and closer to the slope of the tangent line. Take a little bit to look at how mathematicians use the limit to find these rules. This is not something that we're going to work with in much detail at all during this particular unit, but when we do the limits unit, we're going to come back to this. And I just want you to see the origin of the rules that we're about to be working with, and also so you have a little appreciation for how much simpler these rules are than the original way that mathematicians needed to find limits and derivatives. So, let's look at this, finding general rules. So let's say that we have a function. Let's say this function is y equals x squared. It's actually y equals x squared plus 1, but that actually doesn't matter for now, so we'll just keep it simple. Actually, let's make it plus 1 just so you can see why it doesn't matter. Let's say there's some point x. We're going to try to find the slope of the tangent line at this point right here. And we also have some point A. It could be any number. This is just what we're going to use for the dot, for the secant line. Now we've got the little line going through here. And we're going to have our change in y and our change in x for finding our slope. And we know that this point right here is a, and then a squared plus 1. That's the y value. We know that this point here is x, comma, x squared plus 1. We don't know what the value is for a. We don't know what the value is for x. We don't care. We're just trying to find a general rule. So we're saying our big question here is what is the slope of the tangent line at x equals any number. Well, we know that slope is going to be change in y over change in x. And in this case, we find the change in y by simply subtracting this number, subtract that number. So that's x squared minus 1 minus a squared plus 1, whoops. And then the change in x is this x value minus that x value. So this is the slope of the secant line. Slope of the tangent line is the limit of that as this number, a, gets closer and closer to x. So notice up here, this negative is going to distribute here. So we've got positive 1, minus 1, so it goes away, it doesn't matter. We've just got x squared minus a squared over x minus a. Now we can see if we simply plug x in for a, do our substitution, we're going to get x squared minus x squared, which is 0, over x squared x minus x, which is also 0. So this is going to end up with the indeterminate form, 0 over 0, and we know that we can solve that by factoring. If you're a little rusty on this because it's been a summer since you've looked at it, don't worry, we're not going to be doing this in any detail. I just want to show you where it comes from. So we can factor notice that these two factors cancel right out. Limit as a approaches x of x plus a. Now we can just do substitution, except we're doing substitution, so we don't need to write the limit anymore. There we go. So that means that for this equation, y equals x squared plus 1, if we want to find what the derivative is, what the slope of the tangent line is at any value of x, we just take that value of x, multiply by 2, boom, that'll be our answer. After doing this many, 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 many times, mathematicians noticed a pattern. I'm going to write for you what they discovered. Over here we have the function, and over here we have the general equation for the slope of the tangent line. Remember, that's called the derivative. And so I'm going to write what the function was. We just had x squared. And we saw that the derivative was 2x. Well, mathematicians did the same thing for x cubed, and they found the derivative was 3x squared. Same thing for x to the 4th. Found the derivative was 4x to the 3rd. Same thing for x to the 5th. They found the derivative was 5x to the 4th. Etc., etc., etc. And so mathematicians looked at this, and they noticed that, lo and behold, there seemed to be a rule. If there was a function that was just x to the nth power, then all that seemed to be happening was that this exponent became a coefficient. It was brought down in front there, and that 1 was subtracted from the exponent. And these patterns led to the derivative rules that are the focus of this unit. Notice how much easier this is than going all the way through the limit definition. So we're about to get into more detail of what all those rules are that mathematicians spent so long figuring out. Before that, though, a quick caution. These rules can only be used when a function is differentiable. Differentiable simply means you can take the derivative. It's sort of a self-fulfilling prophecy. But in general, what this really means the function must be continuous. That means don't lift your pencil. With no sharp turns. And no vertical tangent lines. Okay,